A divides B is a very important concept. We're going to review the definition and then go through some direct proof involving divides propositions. Let's get started. So you may recall that A divides B is making a statement, a true or false statement, where we say, here's the notation we use, A divides B if I can write B as A times some sort of integer. In this case we use K. So if I can write B as A times K, then that means A divides B. I have another video going over some explicit examples of this if you want to look over examples, but we're going to get into some proofs, so let's go. Alright, so here's my proposition. This time I have three integers, and if A divides B and A divides C, then can we show that A divides the sum of B plus C? So I will do a quick example of this. So I know that 3 divides 6, and I know that 3 divides 9. I know that because I can write 6 as 3 times something, I can write 9 as 3 times something. So that also means then that if I add the 6 and 9 together to get 15, I believe that 3 will divide that sum as well. Now that's true with an example here, but can I prove this in general terms? This is where we have to use the definitions. An example is not enough. Alright, so we will start with a proof. And in my proof, I'm just going to apply the definition. I know that A divides B and A divides C. I get that information for free. And by the way, if you're confused on why that is, anything that follows the if statement but before the then statement, I get that for free. I'm hypothetically assuming that that is true. So I'm assuming here that A divides B and A divides C. Okay. So I'm going to say since A divides B and A divides C, we know B can be written as A times K1 and C can be written as A times K2, where K1 and K2 are integers. Okay, now it might be good to put in some scratch work on the side. What am I trying to say here? I want B plus C to be written as A times some integer. Okay, so that's where I'm going. So I have B equals A times something. I have C equals A times something. So maybe I should add B and C, right? So B plus C then could be written as, how about AK1 plus AK2? And there it is. All I have to do now is factor out the A out of both terms. And I could actually write this as AK, where when I write K, what I mean is the sum of K1 plus K2. So that means that B plus C can be written as A times K. Just use the definition again. That's divides. So by definition, A divides B plus C. And that's it. End of proof. Not too bad. But we have to understand our definitions and apply them. A lot of times students getting started just try to do this with pure logic. And logic is very helpful. I'm not trying to diminish logic. But we need the definitions to communicate this precisely. Otherwise, we get what we call in the math community hand-waving statements. Like, it kind of like, if you think about it this way, you got to be precise with the definitions. Here's another one. Here we have A, B, and C are integers. A squared divides B, and B cubed divides C. I think that means that A to the 6th power divides C. Again, I get to say that A squared divides B, and B cubed divides C, right? So I'm going to start out by saying, let's just let A squared divide B, and B cubed divide C. Now here's a little just proof writing note, because I was tempted just to write A squared divides B. Don't start a sentence in proof writing with a mathematical symbol. So A is a variable, so I don't want to start a sentence with the variable A. So that's why we do a lot of let this, since this. You'll do a lot of hence and thus and therefores. Then you'll see a lot of that language. Okay, so here we're going to let A squared divide B and B cubed divide C. Thus, see, that's what I'm talking about. By definition, B is A squared times K1, and C is B cubed times K2, where K1 and K2 are integers. So I need to somehow put this together and get an A to the 6th power. And I think the trick here is that I'm just going to substitute in B from the first equation into the second equation. So I'll say thus again. I get C is B cubed K2 But I know that b cubed is the same thing as a squared k1. So all of that cubed times k2. And then just following the arithmetic here, you can distribute powers when I'm multiplying. Not when I'm adding, but when I'm multiplying. I get a squared cubed, which is you multiply the exponents together. A to the 6th, k1 cubed, k2. Now k1 cubed, k2 is just some sort of integer. We don't really care what that is. Because the point is we wrote c as a to the 6th times some integer. We'll say where k is this k1 cubed, k2. So that means, if you follow, c is a to the 6th times something. Hence, by definition, what definition are we applying here? The definition of divides. A to the 6th divides c. End of proof. Now we just proved this for every possible case you could come up with. This thing will work. This proposition will work. Alright, I hope this is making sense. Practice makes perfect. You got to keep putting in time. I have another example. Let's take a look. Okay, so this time I have a proposition here that says we're going to let a, b, and c be integers. And I'm saying if 7 divides 8 times a, then 7 divides a. Now I need to think about that for a second. Let's try to come up with an example. So I need 8 times something that 7 divides. So maybe 7 divides 56, for example. And what this is saying, so I can write 56 as 8 times 7, and this is saying that 7 divides 7. Okay, I think that makes sense. How do we prove it? Now, to prove it, we need to add in one additional statement, and that's what I have this lemma here. It's called Euclid's lemma, a very powerful lemma. We might prove it later on, but for now we're just going to say, hey, just trust me on this. And it says that if a divides two things, b times c, but also the greatest common divisor of a and b is 1. So that means that the only thing that divides a and b is 1. If that's true, then a divides c. So it's kind of like I can just get rid of the b and not worry about the b. This greatest common divisor equals 1 also has there's a term attached to that. We say that a and b are relatively prime. So it's kind of like they're prime with each other. They don't have any common divisors other than 1. Okay, so we're going to use Euclid's lemma. We don't have to prove it today. We will later. But we're going to use Euclid's lemma to prove this proposition. So here's how it goes. We're going to say 7 divides 8 times a. Note, what's the greatest common divisor of 7 and 8? The only thing that divides 7 and 8 is 1. So by Euclid's lemma, 7 doesn't divide 8, right? So I can just throw away the 8 and just say 7 divides a. And that's really it. Now this example is different because I actually didn't use the definition of divides. I used another result that we call Euclid's lemma. So that's another part of direct proof. With direct proof we use definitions, logic from the definition, or previous results and the logic following thereafter. So in this case we used a previously proven result even though we haven't proven it. We're just assuming we had already, and then we're going to use that information to show how to get this. If we try to use the definition on this example, it can be kind of difficult. We have 3 examples of proofs involving divides. If you have any questions on this, please let me know. I hope it makes sense. Practice makes perfect. Keep putting in the time. Keep working on it. Again, I hope this is helpful. Thanks for watching, and we'll see you later. Take care.